9, students. We're going to be looking at section 3.5 today, which is about function transformations, transforming all of those parent functions that we learned about in that library of functions from section 3.4. There are a lot of things going on right here. Okay, we have this function f of x, and let's just say that's some parent function. But then we want to transform it. Maybe we want to stretch it, or shrink it, or spin it, or flip it, or shift it. There's all kinds of ways to do those things. And so these letters, the A, the B, the C, and the D, will accomplish the kinds of transformations that we want to make happen. So we're going to tackle those letters one at a time and tell what they do. A is this letter in front of the whole thing. So let's just say if you had, let's say you had f of x equals the absolute value of x. Then A would be any number you put in front of it. So like if f of x were equal to 2 times the absolute value of x, then the A would be 2. All right, and what does that accomplish? That accomplishes a vertical dilation. Now that's just a fancy word for saying a vertical stretch or shrink. So if the normal absolute value is like that, then if the absolute value of A is greater than 1, so here like 2 or 3 or 100, then you have a vertical stretch. It's going to stretch vertically, so it's going to get taller quicker. It's going to be taller and skinnier. If the absolute value of A is less than 1, so if this was a 0.9 or 1/2 or anything like that, then you're going to have a shrink. So it's going to make it vertically go up slower. So it's going to be like this. So it's going to be shorter and wider in that case. If A is negative, then it's going to cause a flip, a vertical flip, also known as a reflection over the x-axis. So these absolute value functions would turn and go the other way. They would flip over that x-axis. All right. So to transform f of x, whatever ordered pairs we have, we're going to multiply each y-coordinate by a. So if we have an xy chart, and we have these numbers in it, then let's just say we were doing the absolute value of x. Let's say we were doing this. First, I wouldn't look at any of the transformations. I'm going to ignore the 2 for now. I'm only looking at the parent function. So look at parent function only at first. Parent function being, in this case, the absolute value of x. And so if we plug -2 into the absolute value of x, what do we get?
2 times 2.
No, just only plugging it into the absolute value of x. 2. If we plug -1 in, what do we get? 1. If we plug 0 in, what do we get?
0.
If we plug 1 in, what do we get?
1.
And then 2 as well. So those are the ordered pairs for the parent function. Then if I have an A in front of it, now I'm going to handle that after I've gotten my original values. I'm going to handle those transformations like that 2 here. What do? Multiply each y-coordinate by A. So all these y-coordinates are going to get multiplied by 2 in this case. So that's going to be now a 4, a 2, a 0, a 2, and a 4. So my ordered pairs would be -2, 4. Sorry, yeah, -2, 4, -1, 2, 0, 0, 0, 1, 2, and 2, 4. So that is this function. so far?
Not yet.
All right. Now we're looking at B. B causes a horizontal dilation. So, if you had that absolute value function, the B would not be found in front of that whole absolute value function, but inside of the absolute value function. So let's say like this. So now that 2 is not A, it's B. If the 2 was in front of the whole thing, it would be A. But if the 2 is inside of that parent function, it's B. And so that doesn't cause a vertical dilation, it causes a horizontal dilation. In other words, a horizontal stretch or shrink. Now inside of the parent function, inside of it, is kind of like opposite land. It does the opposite of what you would think. The A, if the A is greater than 1, it makes it stretch. If it's less than 1, it makes it shrink. The bigger it is, the more stretch you have. But inside the parent function, it's the opposite. If the absolute value of B is greater than 1, it doesn't cause a stretch, it causes a shrink. And the bigger B is, the more of a shrink it is, which is kind of the opposite of what I would tend to think. And so if the absolute value of B is less than 1, it causes a stretch. Now we're talking about stretching horizontally, not stretching vertically. So the smaller B is, the more of a horizontal stretch you have. All right, if B is negative, it causes a horizontal flip. In other words, a reflection over the y-axis, not the x-axis. Okay? So let's take the parent function, the square root of x, and let's transform that to f of x is the square root of 2x and see what happens. In fact, let's make it a negative 2x and see what happens. So the original parent function, by the way, looks like this. Something along those lines. Okay. Let's do a little XY chart. And for the, usually we like to plug in the numbers -2, -1, 0, 1, and 2 for x. But there are a couple of functions where those would not be the smartest numbers to plug in. The square root function and the cube root function would be examples of those where there would be some smarter numbers to plug in. I want to plug in numbers that have perfect square roots into the square root function. So what numbers would be good to plug in that have perfect square roots?
4,
Yep,
9,
4 and 9 are great examples. Now, what about earlier than 4 and 9? 1 would be a great, and 0. Yeah, let's just use those 4. And so if we plug in 0 into the parent function, what do we get? The square root of 0. All right, what if we plug in 1?
1,
What if we plug in 4?
2,
And 9?
3.
Yeah, good. So these are the core values for the parent function of the square root function. Now I'm going to apply the transformation where B is -2. It says in your notes page to transform f of x, multiply each x coordinate by 1 over b. Not by b, but by 1 over b. And I should say, if anybody is at home, not in class watching, you can get this notes page on Moodle. Just look where you see those videos for chapter 3. You'll see a notes page that says function transformations notes page. And this may be revision 2. All right, so multiplying by 1 over b. 2 in this case. So 0 times 1/2 is, actually by 1 over negative 2, sorry, by negative 1/2.
It would be
So 0 times negative 1/2 is still 0. 1 times negative 1/2. What's 1 times negative 1/2? Negative 1/2, right? What's 4 times negative 1/2?
negative 2,
Negative 2. What's 9 times negative 1/2?
negative
Negative 9 over 2, or we might say negative 4.5. Right? So now, what do those ordered pairs look like? So, I got 0, 0. I got negative 1/2, 1. So these are my ordered pairs I'm graphing, by the way. 0, 0, 0, 0, negative 1/2, 1. So negative 1/2, 1 would be here. Right? Negative 1/2, 1. Negative 2, 2. Negative 2, 2. Negative 4.5, 3. Negative 1, 2, 3, 1, 2, 3, 4.5. 3. Okay. So that's my new transform function. And I got those ordered pairs. These are the x coordinates of the ordered pairs. These are the y coordinates of the ordered pairs for the transform function. All right, notice how the parent function,
Okay, do it now.
notice how the parent function is flipped from this way to now this way. And also notice that this would be the parent function flipped if it wasn't, if it didn't have a horizontal shrink. So notice how it is shrunk horizontally. Like this one goes horizontally, it goes horizontal quicker than this one does. This is a little bit slower going horizontally than this one is. So it's like a horizontal shrink. It's a little wider horizontally.
So we get that. Like that.
All right, C causes a horizontal shift. And C is anything that is inside of the parent function added or subtracted inside of the parent function. So let's say if it was, this square root function again. Let's say the square root of x plus 3. And this is, again, this is opposite landing here. I would think that if I'm going to do a plus 3 in there, that I would move it to the right by 3. But it actually moves it to the left by 3. So you move it left to right by negative c. So you add negative c to each x coordinate. So a plus 3 would actually be subtracting 3 from every x coordinate. Whereas if it was like x minus 3, then it would be moving to the right. I would be subtracting negative 3. In other words, adding 3 to each x coordinate. Let's just do a couple of examples to see how that works. All right, again, we're just using the parent function at first. So I'm going to use the numbers 0, 1, 4, and 9 again, since we're dealing with the parent function. We're dealing with the square root function. And so if I'm just doing the square root of x at first, then this is going to be 0, 1, 2, and 3. Because the square root of x, or the square root of 0, 1, 4, 9 is 0, 1, 2, and 3 respectively. Then I'm going to apply this to it. So I'm going to add negative c. C, in this case, is 3. So I'm adding negative 3 then adding negative c to each x coordinate. Another way to say that is just say, or subtract 3. So I am adding negative 3 or subtracting 3, however you want to say that. So 0 plus negative 3 or 0 minus 3 is what?
Negative
Negative 3. 1 minus 3.
negative
4 minus 3.
1.
Sorry, 1, right? Sorry. And 9 minus 3. Yep. So let's look at this graph. So I've got, here are my ordered pairs. My first ordered pair is negative 3, 0. So negative 3, 0 is my first ordered pair. My next ordered pair is negative 2, 1. Negative 2, 1. Then 1, 2. 1, 2. Then 6, 3. 6, 3. Notice that it is the square root function shifted to the left by 3. I'm going to do one more example of C before I go to B. Let's say f of x equals the absolute value of x minus 1. Alright, so we're just going to do our normal xy chart. We're always going to use negative 2, negative 1, 0, 1, 2, except on the square root and cube root functions. So, and I'm just thinking about the absolute value of x only, parent function. Absolute value of negative 2 is 2, absolute value of negative 1 is 1, and then 0, and then 1, and then 2. And then c in this case is negative 1, right? C is negative 1. So I'm going to subtract negative 1. Sorry. Let me say that a different way. I'm going to add negative 1, right? C is negative 1, and I'm adding negative c, so I'm adding negative 1, which is the same thing as adding what?
1.
Adding 1 to all of the x coordinates. I'm just adding 1 to all those, so that's going to be negative 2 plus 1 is negative 1, negative 1 plus 1 is 0, 0 plus 1 is 1, 1 plus 1 is 2, 2 plus 1 is 3. So these are the new x coordinates for my ordered pairs, and the y coordinates haven't changed. So if I graph that, negative 1, negative 1, 2, 0, 1, 1, 0, 2, 1, and 3, 2. So this is just my normal absolute value function shifted to the right by 1. Everybody good with that?
We don't have to do that, probably.
And the last one is D. D is probably the simplest one. It just shifts the graph up or down, and it does it the way you would think. Like if it's plus 3, you shift it up 3. If it's minus 5, you shift it down 5. The difference between C and D is that C is inside of the parent function, D is outside of the parent function. So if it was an absolute value, you'd be adding something outside of the absolute value. If it was a square root, you'd be adding or subtracting something outside of the square root. So let's just say, let's say if it was x cubed. X cubed was the parent function plus 5. Alright? We're just going to do those same -2, -1, 0, 1, 2. And we're just going to use the parent function at first. So then I say -2 cubed. What is -2 cubed?
Negative 8.
-8. Right? -2 times -2 times -2. That would be -8. -1 cubed.
Negative
0 cubed.
1.
1 cubed.
1.
2 cubed.
8.
Okay? Then I apply the transformation of the plus 5 for D. And what do? I just add that to each y coordinate. I add 5, in this case, to each y coordinate. So plus 5, that's going to be -3. That's going to be 4. That's going to be 5. That's going to be 6. And that's going to be 13. So here are my ordered pairs. Those are the x coordinates. Those are the y coordinates. Okay. Let me graph that over here. All right, we got -2, -3. -2, -3. -1, 4. Um, 0, 5. 1, 6. And 2, 13. So this is what we have. And it is just the cube root function shifted up by 5. Okay, now we're going to do an example that puts together all of them at once. We have an A, a B, and a C, and a D all at the same time. Okay, so what we need to do first, if we have a B and a C, we need to get it in this format. A times f of B parentheses x plus C plus D, which is what I had up at the top of that note page. Which means, in order to clarify what B and C truly are, if there's a number in front of that x, you gotta factor that number out. Whatever number's in front of that x, factor it out inside of that parentheses. So that means with this, I'm going to rewrite it as f of x equals 3 times, and then since there's a 2 in front of the x, I'm going to pull a 2 out. And what's left on these two terms, when I pull that 2 out, it'll be x minus 2, right? When I factor out a 2, plus 5. What if it wasn't, like, what if the 2 didn't evenly divide into the other number? Like, you're still going to do this. You're still going to factor out whatever number's in front of there. So, if, like, let's say if you had 5x minus 3 squared, then you would still factor out the 5, and it would leave you with x minus 3/5 squared. So then your B would be 5, and your C would be -3/5. Okay? So that's what I have written here. So now we can distinguish what all of our letters are. A is 3, B is 2, C is -2, and D is 5. So I'm going to apply all those transformations at the same time. Alright, and the way that I would like to do it is go to an XY chart. And then I will apply those transformations to the XY values in the chart. Alright, what's my parent function here? What's the main parent function going on here? Is it linear? Is it x squared, an x cubed, a square root of x? What? It's an x squared. X squared is the main parent function. Even though all these other numbers are happening, the primary parent function that is happening is x squared. So, I'm plugging in -2, -1, 0, 1, and 2. And I'm only plugging them into x squared at first. So if I plug -2 into x squared, what do I get?
4.
If I plug -1 into x squared, what do I get? 0. Yeah, you're right. If I plug -1 into x squared, I get 1. What about 0?
0.
What about 1?
1.
What about 2?
4.
Good. So those are my core values for my parent function. Okay? On the x side, I'm going to be doing two things. And you can see this on your notes page. I'm going to multiply by 1 over b. So what is b in this case?
2.
So I'm multiplying by 1 over 2, and I'm going to add whatever c is. I'm going to add -2, which that means I'm going to subtract 2. So I'm multiplying by 1/2, and I'm subtracting 2 to every number. And I'm doing it in that order, right? The order of operations means I multiply first, then add and subtract. So -2 times 1/2 is what? -2 times 1/2 is -1, and then -1 minus 2 is -3. And you can use your calculator to do this, -2 times 1/2 minus 2. Alright, so I'm just going to go quickly through this. -1 times 1/2 is -1/2. -1/2 minus 2 is -2.5, or -2.5. Okay, 0 times 1/2 is 0, and then minus 2 is -2.
I have a question.
Alright, let me finish this first. 1 times 1/2 is 1/2. Minus 2 is -1.5, or -1.5. Alright, 2 times 1/2 is 1. 1 minus 2 is -1. Alright, go ahead.
It wouldn't be for the, oh wait. Yeah, for C, since C is -2, it wouldn't be, adding to it.
Okay, so I just wanted to test you out, what not to do, to show you a common mistake that's easy to make, even among math professors. Okay, yeah. So something's wrong here, and it is, in fact, a student pointed this out to me just now. Nadia did. Very smart. Thank you, Nadia. Credit to you. What up above here on the notes page it says, what does it say? Add -c, right? Add -c. Well, if c is -2, then I need to add -c, which is -2. I need to add -2, which means I need to just add 2. That is very confusing, but hopefully after seeing me make a fool of myself on that, you will have the benefit of not doing that yourself. So I just need to add 2, not subtract 2. So let me go back through this again. -2 times a half is 1, -1, sorry, -1 plus 2 is 1. -1 times a half is -1/2. -1/2 plus 2 is 1.5 or 1.5. 0 plus 2 is 2.
Why do you put them in point 2?
1 times a half is 1/2. 1/2 plus 2 is 2.5, so that's 2.5. 2 times a half is 1. 1 plus 2 is 3. All right. Okay, so these are my new x coordinates. The b and the c are the only things that change the x coordinates. They're the only things that affect the x coordinates. These are my new x coordinates. Now for the y side. For the y side, it's the a and the d that affect those. What do I do to the y's? I multiply by a and I add d. So I multiply by 3 in this case, and then I add 5. Okay. All right. So 4 times 3 is 12. 12 plus 5 is 17. 3 times 1 is 3. Plus 5 is 8. 0 plus 5 is 5. 1 times 3 is 3. Plus 5 is 8. And 4 times 3 is 12. Plus 5 is 17. These are my new y coordinates. Notice the d and the a and b are easier to deal with usually than the b and the c. For the d, you just add it as it is. For the c, you add the opposite of what you think it is. Okay. So for my new ordered pairs, enough on the x-axis. On the y-axis, I got to go all the way to 17. So I'm going to make it a little shorter. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Okay, so this is not going to be exactly the scale. But I've got 1/17, 1.5, 8, 2, 5, 3, 8, sorry, 2.5, 2.5, 8, and 3/17. Something along those lines. For the graph. All right.
No.
Just to reiterate for C one more time to make it very simple. If C is negative, you're going to add it. If C is positive, you're going to subtract it. All right, I just want to go over a few specific homework problems that I thought were a little extra tough. Question number 10 on 3.5. Find the function that is finally graphed after the following transformations are applied in the order listed to that graph of the square root of x. So I'm just going to, what I'm going to do is I'm going to first figure out what the graph is going to look like after we do these transformations to it. So here's my original square root function. I'm going to shift 8 units up. So now here's my function after that step. Then I'm going to reflect about the x-axis. So here's the x-axis, so we're gonna reflect about that, means we're gonna flip over that axis. So now I'm gonna be down here. I'm down here, and now I'm going that way. So I have flipped this, I flipped it over the x-axis, so that it is now down there at -8, and it's pointing, it's curving the opposite direction, vertically. Okay? Then I'm going to reflect about the y-axis. So I'm taking this, and I'm reflecting it over this y-axis. So it's going to go that way. So it's like, now it's going to be like this. Okay, so this is the final form of the graph. All right, so I'm going to erase these others, or maybe I'll just draw a new graph over here. So that's what I'm trying to get the equation of. Okay? So y equals, what is going to be A? What A, all that has to happen here is a flip. So it needs to be a negative. A needs to be a negative. It's not stretched. It's not like it's going up or down faster. It's just flipped. So A is basically just a -1. So it's just a negative in front of it. All right. It's also flipped over the y-axis. So it's also, B is also -1. It's not a stretch, not a horizontal stretch, but it is a flip. So B is also -1. There is no horizontal shift, so there's no C. So I don't need any parentheses there. So it's just a negative. There's no C, so it's just a -x. But then I am shifted down 8, so B is -8.
What is it? What, it wouldn't be positive, because this is, wait, I'm confused.
Okay, no, it wouldn't be a positive 8 because we're shifted down 8.
Oh, because it reflected on the axis.
It reflected over both axes.
Wait, I'm still confused.
All right, the student's question here was, we thought, well, what about, I thought it shifted up 8. Why is it -8? It's because we had to do these steps in the order they were listed, so we had to shift up 8, but then we reflected about the x-axis, which made the whole thing flip down. And so in reality, the final product here, the final graph, was shifted down 8. So that's why I went through all those steps the first time. I shifted up 8, then I went down there, and so that ended up making it shift down 8 after we reflected over the x-axis. That's why I wanted to do this problem with you, because this can be a confusing thing, because you got to do those transformations in a particular order, which may make the transformations not what they originally were.
So what about,
Okay, I want to look at problem number 11. So it gives us the x-intercepts. The x-intercepts are 3 and 9. Then it says to transform the function by doing this right here, by making it f of x plus 4. What does the x plus 4 do? What is the plus 4? What is that plus 4? A, B, C, or D? It's C. So C is 4. And so I'm going to, which way is it, what's that going to do to the graph?
It's gonna shift it to the right, no, shift it up. Is it down? Down?
Try one more, you got one more direction.
Oh, left.
Left. It's going to shift it left 4. Remember, it's always the opposite of what you think. So like a positive 4 means we're going to shift it to the left by 4. It means we're going to subtract 4 from all the x coordinates. Alright, so then what does that do to the x-intercepts? The x-intercepts are 3, 0, and 9, 0. What is this going to do to those?
It's gonna change it forward. Like,
Yeah, it's going to change the x coordinates. It's not going to change the y coordinates, but it's going to change the x coordinates. So it's going to subtract 4 from both those x coordinates. So the new x-intercepts are going to be -1, 0, and 5, 0. I don't know if it wants you to type in ordered pairs or just type in -1 and 5, but whichever it wants, just give it to it. I think it probably just wants the -1 and the 5. You just type -1, it says use a comma to separate answers, so then put a comma and then put a 5. All right, what if it gave the y-intercept? What if it said the y-intercept is 0, -2? What if it said the y-intercept is 0, -2? What would the new y-intercept be? Well, that would actually be hard to tell because it would change the x coordinate, but it wouldn't change the y coordinate, but then it would no longer be a y-intercept, so you wouldn't be able to really tell what the y-intercept is, so don't worry about that. Let me ask this.
I'm copying.
All right, I'll go back in a second. What if it said, A, what if it said, 3 f of x? It gave the x-intercepts, and then it said, what are the new x-intercepts if you had 3 times f of x? What would that do? What is the 3?
you will multiply it by the y.
Multiply all the y's by 3, right? But then, so you multiply that by 3 and that by 3, but what would happen?
It would just
It would still be 0. So this would not change the x-intercepts at all. The x-intercepts would still be what they are.
No.
All right, continuing on with number 11, part B. What are the x-intercepts if it's f of x minus 2? So what do we do then?
You would
Add 2 to the x coordinates. So that instead of a 3 and a 9 for me, it would be, I would add 2, it would be a 5 and an 11. And then the x-intercepts of the graph of 3 times f of x, we kind of just said what that would do.
3 and 9.
Yeah, it wouldn't change the x coordinates at all, so the x-intercepts of 3 and 9 wouldn't even change from that. It would still be that.
How is yours?
And then, what would this do? This would multiply all the x coordinates by 1 over -1, right? In this case, b is -1. So we'd be multiplying all the x's by 1 over -1, aka just -1. So these x-intercepts negative what then?
Negative.
They'd just be multiplied by negative 1 and be negative 3 and negative 9. Okay, number 18 from the homework. Part A, use a graphing utility to graph f of x equals x cubed minus 4x for x being between negative 4 and 4. So I would want to graph that on my calculator because that's what it wants me to do. X cubed minus 4x is what my function says. X cubed minus 4x. And it says between, for x being between negative 4 and 4. So on my window, I'm going to let my x min be negative 4 and my x max be 4. And I'm going to graph it and see if that is a good graph. Yeah, that's a good graph. So which one of these looks like it's the right graph? C. Notice there on their window they've just got the y going from negative 4 to 4. My y is the standard going from negative 10 to 10, which is why mine looks a little bit different than theirs. Okay, next. Find the x-intercepts of the graph of f. So we can do that by solving by hand. We could set this equal to 0 and solve by hand, or we could just find it on the graph.
Or it's a little bit. Mine's a little bit different. It says
So again, we could find this by hand or on the calculator. So if I do it on the calculator, I can hit second calc, and I'm finding the zeros. That's the same thing as x-intercepts. So if I want to find this x-intercept over here, left bound could be there, right bound could be there, then just hit enter again. And so one of my x-intercepts is negative 2. I bet you can already see what this x-intercept is. It's just going to be 0. And then over here, I think this one's just going to be 2. Now if you want to make sure, if you want to go through the process of second calc and make sure that's a 2, that's totally good to do. But I kind of already know this is going to be negative 2, 0, and 2. So my x-intercepts are negative 2, 0, and 2. Okay, next it says find any local maxima and local minima. It says type an ordered pair round to 2 decimal places. So to do that on my calculator, I hit second calc. I'm going to go ahead and find the maximum first, which is over here. So left bound, that's fine for my left bound. Right bound, just need to go to the right of that hump. Click enter, and then just hit enter again. And my maximum is at negative 1.15, 3.08. Alright, I'm going to go ahead and, well, that says minimum first, so I should have found that first. Alright, I gotta remember what that was. Negative 1.15, 3.08. Now I'm finding the minimum. Okay, left bound, right bound. Hit enter again. 1.15, negative 3.08. 1.15, negative 3.08. And the maximum was at negative 1.15, positive 3.08. Next it says determine where f is increasing and decreasing. Well, knowing these maxima and minima are going to help me determine that. It's going to be increasing at first from negative infinity on the x-axis until we get to that, that maximum, which for me was at negative 1.15 for x. If we're just limited to not negative infinity but negative 4, if we're just talking about from negative 4, then it would be negative 4 to negative 1.15, and then again it increases from here, which would be positive 1.15 all the way to infinity, or we could say all the way to 4 if we're stopping there. And then it's decreasing just here, from here to here. So from negative 1.15 to positive 1.15 on the x-axis is where it's decreasing. Okay, part E. Now, without using the graphing utility, I'm going to repeat those problems, but for a transformation, for f of x plus 1. What does the x plus 1 do?
It's a horizontal shift.
A horizontal shift? Which direction?
Up.
Horizontal is left and right.
Oh, right. So it's left.
Left by 1, correct. Shifts it to the left by 1. So all the x-intercepts that I had before are all going to shift to the left by 1. So instead of negative 2, 0, and 2, now it's going to be negative 4, negative 2, and 0. Actually, sorry, I'm shifting to the left by 1. It's going to be, so everything's going to shift to the left by 1. So it's going to be negative 3, negative 1, and 1. Okay, approximate the local maxima and minima. The local minimum, what was my local minimum before? It was 1.15, negative 3.08. But for f of x plus 1, it's going to shift the x coordinate to the left by 1. It's not going to change the y coordinate. So for me, that's going to be 0.15, still negative 3.08. And my maximum, which was at negative 1.15, 3.08, if I shift that to the left by 1, that's going to be negative 2.15, 3.08. Alright, determine where it's increasing and decreasing. For me, whatever my interval of increase was before, I'm just going to be subtracting 1 from those values. So before, mine was negative 4 to negative 1.15, so now it's negative 5 to negative 2.15, and it was 1.15 to 4, now it's 0.15 to 3, so that's the correct answer for mine. And my interval of decrease before was negative 1.15 to positive 1.15. Well, if I subtract 1 from that, now it's going to be negative 2.15 to 0.15. Next, we are doing the same stuff, answering the same questions. This time, the transformation is 3f of x. What is the 3 going to do?
Multiply.
Multiply what?
Multiply the thing by 3.
Which coordinates, the x's or the y's?
We've been doing the x's. Is it going to be a y?
It's going to be y's, yeah. When A multiplies the y coordinates. So when it says find the x-intercepts of the graph, those x coordinates aren't gonna change at all. They're gonna be the same x coordinates as they were, because multiplying by 3 in front of the whole thing only multiplies the y coordinates. So whatever my x coordinates were before, that's what they are now. So before they were -2, 0, and 2, so they're going to be -2, 0, and 2 again. This time, my local minimum is going to have the same x coordinate it had the very first time, but the y coordinate is going to be multiplied by 3. So let me get my y coordinate before. Let's see here. My local minimum before was 1.15, -3.08. If I multiply that y coordinate by 3, that's going to be -9.24. So 1.15, -9.24. And my maximum was -1.15, +3.08. So it's going to be -1.15 and +9.24. My intervals of increase and decrease, because they are answered by using the x coordinates only, are not going to change a bit from what they were the very first time I answered this question. So -4 to -1.15 and 0 to 1, sorry, -4 to 1.15 and 1.15 to 4 was my answer before, and that's going to be my answer again. And for the decrease, it's just going to be -1.15 to +1.15. This is a long problem.
12 at once?
That's why I want to do it together. All right, now we got the same questions, but for f of -x. What does that do? What does that change? That means b is -1, and we're only changing the x coordinates. All the x coordinates are going to get multiplied by 1 over -1, which is just -1. So all the x coordinates are going to be changing their signs. They're going to be multiplied by a negative. So my x-intercepts before were -2, 0, and 2. Well, if I multiply them all by -1, then it's going to be 2, 0, and -2. So it's going to be the same thing, I guess. So that's -2, 0, and 2. Because the 2 got multiplied by -1 and became a -2, the -2 got multiplied by -1 became a 2, so they're still going to be the same numbers anyway. All right, next it says the local minimum is located at where? So the local minimum is going to change by multiplying the x coordinate by -1. So my local minimum before was 1.15, -3.08. So now it's going to be -1.15, -3.08. All right, and the local maximum, similarly, my local maximum was -1.15, 3.08, but now it's going to be +1.15, 3.08.
This is the same one as the one at the top, isn't it?
All right, for the intervals of increase and decrease, I just want to visualize this. If we reflect this thing over the y-axis, which is what we're doing for f of -x, that means means it's gonna be now like this. Okay, so it's gonna be an interval of decrease where it was an interval of increase, now it's an interval of decrease. And where it used to be an interval of decrease, now it's an interval of increase. And then where it was an interval of increase, now it's again an interval of decrease. So my intervals of increase are now my intervals of decrease, and vice versa. So let's see if we can answer that question. All right, my interval of increase is what my interval of decrease was, which was negative 1.15 to positive 1.15. And my interval of decrease is what my interval of increase used to be. That's going to be negative 4 to negative 1.15 and 1.15 to 4. And we have finally reached the end of number 18. My goodness gracious, what a problem. That problem will put hair on your chest.
I got one
Make a
part
mathematician out of you yet.
I did too.
and I'm not redoing it to get it right.
I don't want.
Now I want to show you one more. This one won't be nearly as long, but it's the last problem, number 19. Because we haven't completed the square quite like this, I don't think, or at least we haven't done it in a long time. Okay, it says complete the square of the given quadratic expression, then graph the function using the technique of shifting. Now, why would it be asking you to do this in this section? It's because this is in standard form for a quadratic equation, but if we can use completing the square, we can get it into what's called vertex form, which is the kind of form that shows what those transformations are, like what we've been learning in this section. So here's how we do it. We write x squared minus 6x, we leave a little space, and then write the plus 5 out to the side. Then, if we can remember how to complete the square, to complete the square, you take the middle number. Does anybody remember?
You have to,
Divide it.
yeah, you divide it by
2.
yeah.
Divide it by 2,
I was about to say something.
and then square it. So cut it in half and square it. That's how you complete the square. So
negative 3 squared.
we're going to, if we cut this in half, that's negative 3, and then square it, that's positive 9. Okay? And I can do that. I can add 9 as long as I make up for it over here. So I'm going to subtract 9 over here. And that'll keep it the same function. Pretty neat little trick. So now, this right here factors how?
2 plus 3.
Nope.
Wait. Oh, wait. It's both of them are 3s.
Yep. Minus 3 and minus 3.
Oh, right, because of negative 3.
So I'm going to write that as x minus 3 squared. And then this part turns into minus 4. So this is how we complete the square. So I'm going to put a 3 right here and a minus 4 right here.
Minus 4. Where did that come from? What is the minus 4?
Alright. So minus 3. Sorry. Just 3 because it's already got a minus in front of it. This is going to be a minus 4. Okay, so now that we've got it in that form, now we can see that it's x minus 3 squared, so that takes the parent function and shifts it to the right by 3, and then plus -4 means it shifts it down by 4. So I'm looking for the parabola that shifted right 3 and down 4, and to me that looks like choice C. And that's it. I think that's enough to go over for this homework and for chapter 3.5. Good luck with all that. See you next time.